A single teaspoon of star weighs as much as a mountain. This is the reality of neutron stars and magnetars, cosmic monsters born from stellar explosions of unimaginable violence. By the end of this journey, you will understand 25 terrifying facts that push the very laws of physics to their breaking point. We will explore how these objects can erase a planet's atmosphere from thousands of light years away, and what mysterious starquakes sound like echoing through a solid crust of nuclear matter. What does the existence of such extreme power tell us about our place in a chaotic universe? That final, furious act of a dying star is not an end, but a transformation of pure cosmic violence. The star's core, no longer supported by the outward push of nuclear fusion, has nothing left to fight its own immense gravity. In less than a second, this core collapses. Imagine the entire mass of our Sun, or one much larger, being squeezed inward with such force that atoms themselves are obliterated. Protons and electrons are forced together, their opposing charges cancelled out, leaving behind a seething ocean of nearly pure neutrons. This catastrophic compression is what creates a neutron star, an object so dense that a single sugar cube of its material would weigh as much as every person on Earth combined. All of that former star, a sphere that could have engulfed the orbit of Earth, is now crushed into a perfect sphere only about 12 miles across. You could drive from one side to the other in under 15 minutes. This is the violent genesis, the moment a star becomes something else entirely. For most neutron stars, this is where the story of their formation ends. But for a special, terrifying class, the conditions are even more perfect for creating a monster. If the infant star is spinning incredibly fast and its newborn magnetic field is perfectly aligned, that field becomes trapped and wound tighter and tighter in the chaotic collapse. This perfect storm of rotation and magnetism gives birth to the most magnetic object in the known universe, a magnetar. Its violent origin is the foundation for every bizarre and frightening property it possesses, leading us directly to the first chilling fact about their incomprehensible reality. That sugar cube would not simply be heavy. It would be a fundamental impossibility, a piece of a reality so warped it breaks every rule of our existence. This is the first terrifying fact, the ultimate density. To understand what this means, we must step away from the star for a moment and look at the atom. An atom is almost entirely empty space. If you enlarge the nucleus of an atom to the size of a marble, the electrons would be whirling around it over a mile away. In a neutron star, that staggering emptiness is completely erased. The collapse is so violent, the gravitational pressure so absolute, that it crushes atoms out of existence. The electrons are forced into the protons, their opposite charges cancelling out, and all that remains is a sea of neutrons packed shoulder to shoulder with no room to breathe. This is why a fragment the size of a sugar cube would weigh 100 million tons, the combined weight of every single person alive on Earth today. That is not just weight, it is a new state of being for matter itself. Under pressures this extreme, the neutrons themselves begin to do strange things. Physicists theorize that deep within the star's crust, the nuclear material might be forced into bizarre shapes they call nuclear pasta. It could form long, thin strands like spaghetti, or flatten into wide sheets like lasagna, structures held together by the strongest force in nature. This is the foundation of everything that follows. Packing the mass of a sun into a city forces matter to behave in ways we can only simulate in equations, and it creates a gravitational field of pure, distilled terror. That impossible density creates a gravitational pull that is the second terrifying fact, a surface gravity that warps reality itself. This force is not merely strong, it is 2 billion times stronger than the gravity we feel on Earth. To stand on the surface would be an instant and total transformation. You would not fall, you would be pulled apart and compressed simultaneously, flattened into a layer of atoms thinner than a sheet of paper before your nerves could even register a sensation. This gravity does not just crush matter, it warps the very fabric of space and time around the star. According to Einstein's theory of general relativity, such immense mass bends the path of light. If you could observe a neutron star from a safe distance, you would witness a bizarre optical illusion called gravitational lensing. The star's gravity acts like a cosmic magnifying glass, bending light from the far side of the star up and over its horizon. This means you could actually see more than half of the star's surface at once, a back and a side simultaneously, a direct visual proof of space-time curving. This crushing force even sculpts the star's own impossibly hard surface. Any irregularity, any bump, is pressed down with the weight of worlds, yet the material is so unbelievably stiff that tiny imperfections remain. These are the mountains on a neutron star. They might rise only a few centimeters high, mere ripples on a 12-mile-wide sphere. But because the material is so dense, that centimeter-tall bump contains more mass than the entire Mount Everest. It is a Himalayan range compressed into a speed bump, held down by gravity strong enough to twist the universe. This constant, unimaginable pressure does not create a quiet, dead world. Instead, it sets the stage for catastrophic internal stress, building up energy until the star's very crust can no longer contain it, leading to events that sound across the galaxy. That perfect crystalline crust is not a peaceful shell. It is a prison of unimaginable pressure, and like any prison under enough stress, it will eventually break. This brings us to the third terrifying fact: starquakes that crack the crust. Beneath the solid surface of a neutron star lies a core of superfluid neutrons, a frictionless quantum liquid that can flow without any resistance. The solid crust, however, spins with the star. Over time, as the star's rotation gradually slows, the two layers begin to slip out of sync. The superfluid core wants to keep spinning at its original speed while the crust drags it down. This builds up immense strain, like twisting a steel spring tighter and tighter until the crust can no longer hold. It fractures. In a single, violent instant called a glitch, the crust shifts and the star's rotation can suddenly speed up by a tiny but measurable fraction. The energy released in that single crack is greater than the total output of the largest solar flare our sun could ever produce. But for a magnetar, this geological event becomes a cosmic catastrophe. The crust of a magnetar is locked in a deadly embrace with the most powerful magnetic field in existence. When that crust fractures and shifts, it drags the magnetic field lines anchored to it. Imagine the entire magnetic field of the star, a structure of unimaginable power, being violently wrenched and twisted like a bundle of rubber bands. This sudden distortion triggers a colossal explosion, a magnetic outburst that can flood space with more X-rays and gamma rays in a tenth of a second than our sun will emit over 100,000 years. We have detected these events from across our galaxy, brief, unimaginably bright flashes that momentarily outshine every other X-ray source in the sky. These are not the quiet deaths of old stars, but the screaming tremors of living, volatile monsters. And if you think the energy from a crack in the crust is frightening, it is merely a spark compared to the true fury of the magnetic field itself. The magnetic field of a magnetar is not just strong, it is a force of pure annihilation. This is the fourth terrifying fact: a magnetic grip so powerful it redefines the possible. While all neutron stars possess ferocious magnetic fields, a magnetar's is in a league of its own, up to 1,000 times more intense. To grasp this scale, consider a typical neutron star's field. If you brought a neutron star to within 100,000 miles of Earth, its magnetic field would be strong enough to erase every hard drive, every credit card, and every piece of magnetic storage on the planet. A magnetar would do the same from a distance of 240,000 miles, the average distance to our moon. Its influence is not a gentle pull, it is an eraser of information, a scrambler of the fundamental order we rely on. But this is just a side effect of its true, terrifying power. The energy stored in a magnetar's magnetic field is so incomprehensibly vast that it can literally tear matter apart at the atomic level. At a certain distance from the star, the magnetic force becomes stronger than the chemical bonds holding atoms together. Any object, any cloud of gas, any stray asteroid that wanders too close does not simply get crushed by gravity. It gets disassembled, electrons are ripped from their orbits, and nuclei are stripped bare, creating a seething, chaotic fog of charged particles called a plasma. This plasma is then trapped, forced to dance along the star's twisted magnetic field lines, glowing with X-rays and gamma rays. This magnetic dominance is the puppet master behind every bizarre thing a magnetar does. It stresses the crust to the breaking point, causing the starquakes we discussed. It channels unimaginable energies into focused beams, and it creates an environment so hostile that it can produce an event of such sheer, blinding luminosity that for a brief moment it can outshine every star in our galaxy combined. That magnetic field does not just quietly hum with energy, it can scream across the cosmos in a single, blinding flash. This brings us to the fifth terrifying fact, the power of giant flares. On December 27, 2004, a magnetar known as SGR-1806-20, located 50,000 light-years away on the far side of our galaxy, did something unimaginable. In 1/10 of a second, it released a giant flare of gamma radiation so powerful that, for that fleeting instant, it was brighter than the full moon in our sky and outshone every other cosmic event humanity has ever recorded, except for the Big Bang itself. The energy it unleashed was equivalent to everything our sun will radiate over 150,000 years, all focused into a blink of an eye. The effects were felt right here on Earth. The intense burst of radiation ionized the upper layers of our atmosphere, causing a sudden and significant disturbance in the ionosphere. This temporary disruption scrambled long-range radio communications around the planet, a subtle but chilling reminder that events from halfway across the galaxy can reach out and touch our technology. Scientists believe these flares are the ultimate result of the magnetic field's unbearable stress. The field lines, twisted beyond their limit by the shifting crust, suddenly snap and violently reconnect, like a cosmic rubber band breaking and lashing out. In that catastrophic rearrangement, a torrent of energy is channeled into two narrow, opposing beams of pure gamma rays. If one of those beams were pointed directly at Earth from a nearby magnetar, the consequences would be severe, potentially stripping away our protective ozone layer and causing a planetary catastrophe. The 2004 event was a warning shot, a distant demonstration of a power that can bridge galactic distances and remind us that the universe is not a quiet, static place, but a dynamic arena where stellar monsters can flicker with the light of 100,000 suns. And while we were fortunate that beam was not aimed directly at us, it raises a profound question: what would happen if one was? The 2004 event was a stark demonstration of power, but its beam was aimed safely away from us. This leads to the sixth terrifying fact, the threat of a nearby burst. While the probability is vanishingly small, astronomers must consider a scenario where a magnetar within a few thousand light-years of Earth unleashes a giant flare directly at our planet. The consequences would not be a simple light show. The torrent of high-energy X-rays and gamma rays would violently interact with our upper atmosphere, breaking apart the molecules of our protective ozone layer. Without that shield, the surface would be bathed in the sun's unfiltered ultraviolet radiation. the effects would cascade through ecosystems, damaging the fundamental building blocks of life in plants and plankton, and potentially triggering a planetary-scale crisis for living things. This is not science fiction, but a legitimate, though extremely unlikely, cosmic hazard that the scientific community models and studies. We know of magnetars like 1E 1048.1-5937 that exist in our galactic neighborhood, close enough in astronomical terms to be considered part of our local environment. Their existence means the risk is not zero. It is a sobering reminder that our survival on this pale blue dot depends on a fragile balance, and that the universe harbors forces capable of disrupting that balance from incredible distances. This potential for disruption connects to a more common, yet still mysterious, form of radiation these objects emit, one we detect as fleeting, powerful bursts of radio waves that have puzzled scientists for decades. The giant flare from 2004 was a warning shot, but the true danger of these objects is not just in their explosive outbursts. It is in the permanent, invisible hellscape they create around themselves. This is the seventh terrifying fact, the lethal proximity and radiation zones that make their immediate space a realm of pure annihilation. The environment around a neutron star is not empty or dark in a conventional sense. It is bathed in a constant, seething bath of deadly radiation, primarily X-rays and gamma rays. These are not the gentle rays of sunlight, but high-energy particles that can shatter the complex molecules essential for life, like DNA, with ease. For any hypothetical spacecraft or planet, there is a boundary of no return known as the Elfvane radius. Inside this zone, the star's magnetic field is so dominant that any stray gas or particles are caught, accelerated to nearly the speed of light, and whipped into a frenzy. This creates a permanent storm of relativistic particles, a sandblaster of atomic destruction that would strip away atmospheres and irradiate surfaces down to the bedrock. For a typical pulsar, this deadly zone extends for thousands of kilometers. But for a magnetar with its thousand-fold stronger magnetic field, the Elfvane radius can balloon to encompass a region larger than our entire solar system. Picture this, an invisible sphere of lethal energy with a diameter stretching from the Sun out past the orbit of Pluto. Anything within that vast volume exists in a state of constant, sterilizing bombardment. This is why the search for habitable worlds never looks toward these stellar remnants. They are not just dead stars, they are engines of permanent desolation, capable of rendering an area of space the size of a star system utterly inhospitable. This invisible barrier is a stark testament to their power, a force that does not just destroy in flashes, but maintains a quiet, eternal quarantine around itself. And within that forbidden zone, the star's own surface is undergoing processes even more bizarre, where the very rules of matter and light are rewritten by the magnetic field's impossible strength. The star's surface is not a static landscape, but a blur of impossible motion. This is the eighth terrifying fact, a spin so fast it defies comprehension. In the final moments of a supernova, as the star's core collapses from a sphere millions of miles wide to a city-sized object, a fundamental law of physics takes over: conservation of angular momentum. It is the same principle that causes an ice skater to spin faster when they pull their arms in. The dying star's original, slow rotation is amplified to a staggering degree, launching the newborn neutron star into a frenzied pirouette. The fastest known pulsar, named PSRJ 1748-2446 AD, spins an astonishing 716 times every single second. At its equator, the surface is hurtling through space at roughly 1/4 the speed of light. This is not just fast, it is a velocity that begins to challenge the very fabric of spacetime around it. At such speeds, the centrifugal force trying to fling material outward is almost strong enough to overcome the unimaginable gravity holding the star together. It exists in a state of perfect, violent tension, a sphere stretched to its absolute limit. This furious rotation does more than just create a dizzying spectacle. It powers one of the most iconic behaviors of these objects. The star's intense magnetic field channels radiation from its poles into two narrow, lighthouse-like beams. As the star spins, these beams sweep across the cosmos. If one happens to cross Earth's line of sight, our telescopes detect a rhythmic pulse of radio waves, a cosmic heartbeat with a precision that rivals our best atomic clocks. We call these objects pulsars, the ticking remnants of dead stars. Yet this incredible spin is not eternal. It is a wound-up spring slowly, inevitably unwinding, and the energy lost in that slowdown has terrifying consequences for anything nearby. That furious spin is a finite resource, a reservoir of energy being steadily drained away. This is the ninth terrifying fact, the breaking power of magnetic drag. Every neutron star is essentially a colossal spinning magnet, and as it rotates, its intense magnetic field acts like a cosmic anchor plowing through the thin gas of interstellar space. This interaction creates a powerful drag, gradually but relentlessly sapping the star's rotational energy. The process is called magnetic braking, and it transforms the star's spin into something else, a steady torrent of electromagnetic radiation and a fierce wind of high-energy particles that stream out from its poles. For a typical pulsar, we observe this as a steady, faint glow in X-rays, the quiet hum of a cosmic engine slowly winding down. But for a magnetar, this process is not quiet at all. Its magnetic field is so unimaginably strong that the braking effect is thousands of times more powerful. A magnetar's furious rotation can be slowed to a comparative crawl within just a few thousand years, a mere moment on the cosmic clock. This rapid slowdown means the energy being converted is not lost. It is violently released into the surrounding space, powering the star's persistent X-ray glow and contributing to the intense stress on its crust. This creates a distinct life cycle of cosmic drama. A magnetar's youth is a period of extreme violence and hyperactivity, marked by frequent starquakes and outbursts as it bleeds off its immense rotational energy. Only after this frenetic phase, once the magnetic drag has done its work and the spin has significantly slowed, does the monster begin to quiet down, entering a longer, more stable, but no less dangerous older age. This constant conversion of motion into raw power is the engine behind its terrifying behavior, a direct link between its impossible magnetism and the cataclysmic events we witness from across the galaxy. The furious spin of a magnetar is not just a local phenomenon, it may be the engine behind signals that cross the void between galaxies. This brings us to the 10th terrifying fact, the mystery of fast radio bursts. For over a decade, astronomers have been picking up fleeting, powerful blips of radio energy from the distant cosmos. These fast radio bursts last only a few thousandths of a second, yet in that blink of an eye, they release more energy than our sun does in 80 years. Their source was one of astronomy's greatest puzzles, appearing to come from billions of light years away. The leading suspect for creating such a concentrated, titanic flash of power has always been an object of extreme physics, and magnetars fit the profile perfectly. The theory gained stunning credibility in April 2020. A known magnetar within our own Milky Way galaxy, named SGR 1935+2154, entered an active phase. As it crackled with X-rays, it did something unprecedented. It emitted a short, intense burst of radio waves that matched the signature of an extragalactic fast radio burst. This was the smoking gun, the first direct evidence linking these cosmic enigmas to a specific type of stellar corpse. The implication is staggering. If a relatively quiet outburst from a magnetar in our own backyard can produce such a signal, then the truly colossal fast radio bursts we see from other galaxies could be the death cries of magnetars in their most violent, apocalyptic moments. It means these objects are not just monsters of our galaxy, they are universal phenomena capable of projecting their raw, destructive power across intergalactic distances. Their influence and their threat operates on the scale of the entire cosmos. Deep within that city-sized sphere, matter behaves in ways that defy all earthly logic. This is the 11th terrifying fact, the realm of internal superfluids and quantum tornadoes. Beneath the incredibly dense crust we have discussed lies a core that may exist in a state of pure quantum strangeness, a superfluid. On Earth, superfluids are delicate curiosities created in labs at temperatures near absolute zero. In a neutron star, this frictionless liquid is not a tiny sample, but an ocean of nuclear material spanning miles, existing at temperatures of millions of degrees. Here, the neutrons themselves lose all individual identity and flow together as a single, coherent quantum entity with zero viscosity. They can creep up the walls of their container, they never slow down, and they can rotate in ways that solid matter simply cannot. This creates a bizarre internal architecture. The solid crust spins at one rate, locked to the star's observable rotation, but the superfluid core beneath it can spin independently, like a whirlpool inside a sealed jar. Over time, as the crust slows due to magnetic braking, the superfluid core can remain spinning faster, storing immense rotational energy. This builds up a dangerous tension. Eventually, this quantum tornado can suddenly transfer a massive jolt of its angular momentum up into the solid crust above it. When this happens, the entire star's rotation can speed up in a fraction of a second, an event astronomers call a glitch. We have observed pulsars suddenly spinning faster by a tiny but measurable amount, a direct signal of this internal upheaval. It is as if the heart of the star has its own will, occasionally lashing out and changing the body's rhythm. This makes a neutron star the only place in the universe where we can witness quantum mechanics, the rules of the impossibly small, playing out on a scale of miles. It is a unique and violent laboratory for the most extreme states of matter, governed by forces we can only theorize about from the safety of our planet. But even the bizarre superfluid core of a neutron star may not be the final word on density. The 12th terrifying fact pushes theoretical physics into a realm of pure speculation, the possibility of quark stars. We have seen how immense pressure crushes atoms into neutrons, but what if the pressure inside the most massive neutron stars is even greater? Some equations suggest that under such extreme conditions, the neutrons themselves could be shattered. They would break apart into their most fundamental building blocks, particles called quarks. This would create a new, even denser state of matter, a soup of free-flowing quarks that physicists call strange matter. A star made of this material would be a quark star, an object so compact it makes a neutron star seem almost spacious. The theoretical properties of this strange matter are where the true unease begins. Some models suggest that once formed, this quark-gluon plasma could be the most stable form of matter in the universe, more stable than the protons and neutrons that make up our world. And if that is true, a single droplet of strange matter could, in theory, act like a cosmic contagion. Upon contact with normal atomic matter, like a planet or another star, it could catalyze a runaway conversion, transforming everything it touches into more strange matter. This process would continue until the entire object was transmuted. While this remains a speculative and highly debated idea with no experimental proof, the mere theoretical possibility adds a profound layer of existential dread. It suggests a universe where certain forms of matter are not just dangerous but potentially predatory. Astronomers have searched for real-world candidates, objects that seem just a bit too small and dense to be neutron stars. One object, called XTEJ 1739-285, was observed spinning at over 1,000 times per second, a rate so extreme it might only be possible if the star was made of this frictionless quark soup. While not confirmed, these tantalizing hints remind us that our understanding of matter under ultimate pressure is incomplete. The family of stellar corpses may have a member even more extreme and unsettling than the monsters we have already met. Theoretical quark matter may be the ultimate density, but neutron stars can also create a more tangible form of cosmic disturbance. These stellar remnants are not isolated tombs, they can be gravitational wave factories. When two neutron stars become locked in a binary dance, their relationship is one of inevitable doom. Orbiting each other at incredible speeds, they are constantly losing energy. This energy does not vanish, it is radiated away as ripples in the very fabric of spacetime itself, gravitational waves. As these waves carry energy away, the two stars spiral closer and closer together, their orbits tightening in a fatal embrace. This process can take millions of years, but the final act is over in a heartbeat. When they finally merge, the collision is not a simple crash, it is a kilonova, an explosion of light and matter 1,000 times brighter than a typical nova. This event forges the heaviest elements in the universe. Inside the unimaginable heat and pressure of the merger, neutrons are rapidly captured, building atoms far heavier than iron. This is the cosmic alchemy that creates gold, platinum, and uranium, scattering these precious metals across space to later be incorporated into new stars, planets, and even the rings on our fingers. We have witnessed this directly. In August 2017, gravitational wave observatories detected a signal named GW170817. For the first time, astronomers saw the ripples from two neutron stars colliding, and telescopes around the world and in space swiveled to catch the resulting flash of light. The data was a perfect match, confirming that these violent mergers are the universe's primary foundries for the heaviest elements. The gravitational waves from such an event are a physical distortion of reality. As they pass through Earth, they stretch and compress space itself by a minuscule amount, a fraction of the width of a proton, a whisper of the collision's violence traveling for 130 million years to reach our detectors. This makes neutron stars active sculptors of the cosmos, not only through their radiation and magnetic fury, but by literally shaking the foundations of space-time and seeding the galaxy with the very elements that make rocky worlds and complex chemistry possible. The gold on your finger was forged in a stellar collision of apocalyptic scale. This is the 14th terrifying fact, the kilonova blast that creates and destroys in the same instant. We have seen how the merger of two neutron stars sends gravitational waves through the cosmos and forges heavy elements, but that creative act is inseparable from an explosion of pure annihilation. A kilonova is one of the most energetic events in the known universe, second only to a supernova. The collision unleashes a directed beam of gamma rays so intense it could outshine an entire galaxy for a few seconds. This gamma-ray burst is the most immediate and lethal threat. If such a beam were pointed at a planet within several thousand light-years, the effects would be catastrophic, stripping away its atmosphere and bathing its surface in sterilizing radiation. Yet the danger does not end with that initial flash. The explosion creates a rapidly expanding cloud of radioactive debris, elements like platinum, gold, and uranium freshly minted in the blast. This cloud glows brightly across the entire electromagnetic spectrum, from X-rays to radio waves, for days or weeks. This lingering afterglow would continue to irradiate any planetary systems within a sphere of space dozens of light-years across, a prolonged cosmic event that could disrupt climates and chemistry for generations. While these events are thankfully rare in any given galaxy, occurring perhaps once every 10,000 to 100,000 years, their existence means the universe periodically cleanses its neighborhoods with fire. It is a profound duality, the The very cataclysm that could end a world is also the sole source of the precious metals that have shaped human civilization, art, and economy. Your jewelry is not just metal, it is stardust, but stardust born from the most violent divorce imaginable between two dead stars. This link between human adornment and cosmic violence leads us to consider the ultimate fate of these stellar monsters and what happens when even a magnetar's power begins to fade. That gold was forged in a fire of impossible heat, but the forge itself is even hotter. The 15th terrifying fact is the star's own surface temperature, a lingering inferno that defies its dead state. While the nuclear furnaces in their hearts have gone silent, neutron stars are far from cold. Their surfaces rage at over 1 million degrees Celsius, nearly 200 times hotter than the surface of our Sun. This blistering heat is not the product of ongoing fusion, but a trapped echo of the star's violent birth. It is the residual thermal energy from the supernova explosion itself, a fireball of such magnitude that its warmth is still bleeding out billions of years later. Furthermore, deep within the ultra-dense core, exotic particles are constantly created and decay in a slow, subatomic simmer, adding a steady trickle of heat to the interior. This combination makes neutron stars, and especially magnetars, brilliant beacons in the X-ray sky. They glow with the light of a trapped apocalypse, a fossilized heat that will take eons to dissipate. This leads to a profound and chilling cosmic timeline. Over hundreds of billions of years, these stellar embers will gradually radiate their remaining energy away into the void. They will cool, dim, and fade from brilliant X-ray sources to faint infrared ghosts, and finally to invisible, cold spheres of pure nuclear matter. Astronomers call this theoretical end state a black dwarf, a dark crystal of carbon and oxygen for white dwarfs, or for neutron stars, an even denser cinder of degenerate neutrons. No black dwarf is believed to exist yet in our universe, as it would take far longer than the current age of the cosmos for even the oldest stellar remnants to cool completely. This ultimate fate is a quiet bookend to a life of extreme violence. It represents the final, irreversible victory of entropy, the long, slow sigh of the universe as even the most energetic objects surrender their heat to the endless cold of expanding space. It is a reminder that every epoch, from the blinding flash of a supernova to the magnetic fury of a magnetar, concludes with the same line, a gradual dimming into absolute zero. Yet, while this is the ultimate end, the journey there is marked by one last, bizarre property of their unimaginable density, a characteristic that allows them to act as the universe's most precise timekeepers. That precise spin and searing heat do not simply fade into the void, they actively sculpt their own tombs. This is the 16th terrifying fact, the pulsar wind nebula phenomenon. When a young, fast-spinning neutron star is born, it does more than just beam radiation into space, it also blows a fierce, continuous gale. This is the pulsar wind, a supersonic stream of charged particles, primarily electrons and positrons, ripped from the star's surface and accelerated to nearly the speed of light by its intense magnetic field and rapid rotation. This wind is a hurricane of pure energy, but it does not travel forever. It soon slams into the slower-moving debris of the star's own supernova remnant, or the general gas and dust of interstellar space. The collision is catastrophic and beautiful. The particles, forced to a sudden stop, release their immense kinetic energy as light, causing the entire cloud to glow across the electromagnetic spectrum. This creates a luminous, often intricate structure called a pulsar wind nebula, a final, radiant shroud for the stellar corpse at its center. The most iconic example is the Crab Nebula, the expanding remnant of a supernova witnessed on Earth in the year 1054. At its heart spins the Crab pulsar, rotating 30 times per second, its relentless wind inflating and illuminating the entire nebula we see today. These nebulae are not serene clouds, they are maelstroms of chaos. Within them, magnetic fields are tangled and amplified to incredible strengths, and particles are whirled in vast, turbulent motions. They act as nature's most powerful particle accelerators, far exceeding anything we can build on Earth. It is within these glowing cauldrons that many of the cosmic rays, high-energy particles that constantly rain down on our galaxy, are believed to be born and launched into interstellar space. This means a neutron star's influence does not end with its death or its occasional outbursts. It becomes a permanent, active engine, pouring its remaining rotational energy into its surroundings for thousands of years, creating structures of stunning beauty that are, at their core, monuments to relentless, high-energy violence. That glowing nebula is a monument to a star's violent past, but the object at its center faces an even more violent future. Every neutron star exists in a state of permanent, precarious tension, balanced on the very edge of oblivion. This is the 17th terrifying fact, the limit of maximum mass. There is a strict cosmic rule, a theoretical boundary known as the Tolman-Oppenheimer-Volkoff limit. This is the ultimate weight limit for a neutron star, estimated to be between 2 and 3 times the mass of our Sun. If a neutron star's mass creeps beyond this critical threshold, there is no force in the universe that can save it from total collapse. The only thing holding the star up against its own crushing gravity is a bizarre quantum mechanical principle called neutron degeneracy pressure. Think of it as the ultimate subatomic rebellion. The laws of quantum physics forbid neutrons from occupying the same quantum state in the same place. As gravity tries to squeeze them closer together, this rule creates a powerful outward push, a final, desperate stand against collapse. It is the last line of defense, but this defense has its limits. If additional matter, perhaps from a companion star or interstellar gas, falls onto the neutron star, the extra mass increases the gravitational pressure. Eventually, if the star crosses the Tolman-Oppenheimer-Volkoff limit, neutron degeneracy pressure is overwhelmed in an instant. The balance shatters. In less than a second, the entire structure gives way, and the star vanishes from the observable universe, leaving behind only an event horizon, a black hole. This means every single neutron star and magnetar we observe is literally the last possible stable form a star can take before reaching the point of no return. They are not just dense objects, they are cosmic tightrope walkers, perpetually one meal away from disappearing forever into the absolute darkness of a singularity. Their entire existence is defined by this knife-edge equilibrium, a reminder that stability in the cosmos is often a temporary and violently enforced condition. The knife edge of stability defines their existence, but it is their gravity that truly warps reality. The 18th terrifying fact is time dilation at the surface, a direct and measurable twisting of time itself. Einstein's theory of general relativity tells us that gravity does not just pull on objects, it stretches the very fabric of spacetime. The stronger the gravity, the more time slows down. On Earth, this effect is so tiny it requires atomic clocks to detect. On a neutron star, it is a profound, tangible force. A clock placed on the surface of a typical neutron star, one with twice the mass of our Sun, would tick about 20 to 30% slower than a clock far out in space. This is not a theoretical trick, it is a physical reality. An astronaut in a hypothetical, indestructible ship in a close orbit around such a star would experience time passing at this slower rate. For every 100 years that passed for distant observers on Earth, that astronaut might only age 70 or 80 years. They would return to a future where everyone they knew was gone, having lived a slower, distorted lifetime while the universe marched on at its regular pace. This warping is a silent, invisible consequence of the star's impossible density, proving that these objects do not merely exist in space, they actively reshape the dimension of time in their vicinity. It is a subtle but staggering demonstration that the universe's rules are not rigid, but flexible under extreme pressure, bending to the will of a city-sized sphere with the heart of a sun. The warping of time is a silent consequence of their gravity, but some neutron stars actively broadcast their presence with beams of pure annihilation. The 19th terrifying fact involves the riddle of antimatter jets. In certain binary systems, a neutron star orbits a living companion star. Its immense gravity acts like a cosmic vacuum, relentlessly stealing gas from its neighbor. This stolen material does not simply fall onto the star's surface. It spirals inward at incredible speeds, forming a superheated, glowing disk of plasma around the star's equator. Within this chaotic maelstrom, something extraordinary happens. Complex interactions between the infalling matter and the star's monstrous magnetic field channel some of this material not downward but outward. From the magnetic poles of the star, focused beams of particles are launched into the void at nearly the speed of light. These are not ordinary jets. They are composed of electrons and, astonishingly, their antimatter counterparts, positrons. A positron is identical to an electron in every way except for one crucial detail: its electrical charge is positive. When matter and antimatter meet, they do not simply collide. They annihilate each other in a flash of pure energy, converting their entire mass into radiation according to Einstein's famous equation. These jets, stretching for light years into the darkness, are therefore rivers of potential destruction. They demonstrate that neutron stars can be prolific factories of the universe's most reactive and rare substance. The process of how these jets form, accelerate, and remain so tightly focused over such vast distances remains one of the great puzzles in high-energy astrophysics. It suggests a level of magnetic and gravitational engineering far beyond our current understanding, where a stellar corpse can take stolen matter and forge it into lances of opposing reality that stab through the galaxy. This capability adds a profound and dangerous layer to their nature, proving they are not just consumers of matter, but alchemists that can transmute it into its most volatile and explosive form. Even the most powerful magnetic fields in the universe cannot last forever. The 20th terrifying fact is the slow, inevitable decay of a magnetar's defining power. These titanic fields, born from the chaotic spin of the collapsing core, are not permanent fixtures. Over thousands of years, they gradually fade, dissipating their energy into the surrounding space. This decay is not a quiet dimming. It is an active process that releases immense heat, keeping the star's surface at those blistering million-degree temperatures long after its birth. More dramatically, this fading power can trigger one last gasp of violence. As the field weakens and rearranges itself, it can stress the crust anew, potentially causing final, sporadic bursts of X-rays and gamma rays long after the star's hyperactive youth has passed. It is a long, slow death of its most fearsome attribute, a reminder that even cosmic monsters are bound by time. Yet, while it lasts, this magnetic field does something to light itself that reveals its true strength. In any lab on Earth, a strong magnet can subtly split the spectral signature of an atom, a phenomenon called the Zeeman effect. It is like taking a single musical note and forcing it to sing at two slightly different pitches. Around a magnetar, this effect is not subtle. The magnetic field is so strong it can rip these atomic spectral lines apart, splitting them by an amount millions of times greater than anything we can create. This extreme magnetic splitting is so pronounced that, in theory, astronomers could use it to directly measure the field's nightmarish strength just by analyzing the starlight. But more importantly, it means the very environment near the star is a place where the ordinary rules of atomic physics are completely overthrown. Atoms cannot hold their shape, their electrons are torn from their orbits, and their identity is scrambled by a force that treats the building blocks of matter as mere suggestions. This is the ultimate magnetic domination, a realm where magnetism does not just influence matter, it dictates its very existence. The universe has proven planets can form even in the graveyard of a star. The 21st terrifying fact reveals the existence of pulsar planets, cosmic orphans in the ultimate dead zone. The very first exoplanets ever discovered, back in 1992, were not found orbiting a sun-like star. They were found circling a pulsar named PSRB 1257+12, a millisecond pulsar spinning over 160 times per second. This discovery was a profound shock to astronomers, challenging the assumption that planets required the calm, nurturing environment of a stellar nursery. These worlds are not survivors from the star's previous life. They are phoenixes born from catastrophe. They likely coalesced from a swirling disk of debris, the ashes of the companion star that was utterly destroyed by the supernova or slowly consumed by the pulsar's gravity. Imagine a world assembled from the dust of an apocalypse, its very bedrock forged in annihilation. The reality for any planet in such a system is one of permanent, sterilizing siege. It orbits not within a warm, yellow glow, but within the lethal crossfire of the pulsar's lighthouse beams and its relentless particle wind. The surface would be scoured by radiation that shreds complex molecules, bathed in a constant hail of high-energy particles, and subjected to dramatic temperature swings as it rotates in and out of the deadly beam. There is no night that offers respite, only varying degrees of bombardment. These are not worlds in any habitable sense. They are stark demonstrations of cosmic endurance, proving that planet formation is a robust process. Yet their existence also paints a chilling portrait of absolute desolation. They showcase the final, sterilizing power of a neutron star, its ability to not only destroy a solar system, but to then sculpt new worlds from the wreckage that are, from their first moment, eternal monuments to its lethal influence. The silent void of space holds a secret symphony locked within the heart of a stellar corpse. This is the 22nd terrifying fact, the sound of a neutron star. In the perfect vacuum between worlds, sound has no medium to travel, so the cosmos is eternally silent to our ears. But within the ultra-dense, solid crust and liquid core of a neutron star, vibrations can and do race through the material at incredible speeds. When a starquake cracks the crust, it sends seismic waves ringing through the star's interior like a bell struck by a cosmic hammer. These are not gentle ripples. They are oscillations in a medium of nuclear matter, vibrating at frequencies hundreds of times per second, far above the range of human hearing. To translate this hidden activity into something we can perceive, scientists have taken a remarkable step. Using data from X-ray telescopes that detect the subtle changes in a star's brightness as it rings, they have mathematically shifted these ultra-high frequency vibrations down into the audible range. The result is not a melody but something deeply haunting. The translated sounds are low, resonant drones and eerie, pulsing tones that seem to echo from a place of pure density. They sound less like music and more like the deep groaning of a colossal machine under impossible stress, the fundamental note of matter pushed to its absolute limit. This sonic window is far more than a curiosity. By studying the precise frequencies of these oscillations, astrophysicists can peer into the star's internal structure in a way light alone cannot reveal. The way the star vibrates tells them about the stiffness of its crust, the density of its core, and the behavior of the mysterious superfluid within. Each tone is a direct probe into a realm of physics we can never visit, a ghostly echo carrying secrets from the heart of a monster. It is a profound reminder that these objects are not static tombstones, but dynamic, resonant worlds, singing a song of their own violent nature into a silent universe. That ghostly song of vibration is a testament to their incredible rigidity, a property that transforms them into something far more than monsters. Their steady, predictable spin makes them the most reliable clocks in the cosmos. This leads to the 23rd terrifying fact: their potential role as the ultimate galactic navigation system. The pulses from a rotating neutron star, a pulsar, arrive with a rhythm more precise than the finest atomic clocks we can build on Earth. This is not a gentle ticking, but a metronome set by the physics of a 2-billion-ton sugar cube, an object so stiff and unyielding that its rotation barely changes over centuries. This phenomenal stability has inspired a visionary idea for the distant future of space travel, a pulsar-based galactic positioning system. For a spacecraft venturing between the stars, traditional methods like looking at familiar constellations would fail utterly. The familiar sky would be completely alien, but pulsars are visible across the galaxy, and each one has a unique signature, a fingerprint defined by its precise pulse period and location. By listening to the rhythmic beats from a network of these cosmic lighthouses, a ship's computer could perform a form of interstellar triangulation. It would compare the exact arrival time of pulses from 3 or 4 known pulsars against a master chart. The tiny differences in when each pulse arrived would allow the computer to calculate the ship's position in 3-dimensional galactic space with astonishing accuracy, potentially down to a few kilometers even across light years of emptiness. The profound irony is inescapable. The very qualities that make neutron stars terrifying, their crushing gravity and nuclear rigidity, are what make them potentially invaluable. A tool for future exploration is born from the corpse of a stellar catastrophe. It means that if humanity ever learns to sail the ocean between stars, our charts may not be drawn in ink, but in the relentless, deadly heartbeat of long-dead suns. This practical possibility forces us to see these objects in a dual light, as both a lethal hazard and a celestial guidepost, a reminder that in the universe, the line between a landmark and a landmine is often terrifyingly thin. That same heartbeat that could guide a starship also holds the power to silence it forever. This brings us to the 24th terrifying fact: the invisible threat to spacecraft and astronauts. For any future mission venturing beyond the protective bubble of Earth's magnetosphere, the galaxy is not a serene void. It is a sea threaded with lethal currents, and neutron stars are among their most potent sources. The danger is not a dramatic collision, but a silent, insidious bombardment. Even a chance encounter with the relentless particle wind streaming from a relatively nearby pulsar could shower a spacecraft with a flood of high-energy radiation. Modern shielding, designed for the general background of space, might be utterly inadequate against such a focused torrent. The particles would penetrate the hull, delivering a potentially lethal dose to any crew inside, damaging sensitive electronics and scrambling the very biological instructions within human cells. This risk is magnified 1,000-fold by the unpredictable nature of magnetars. A single directed burst from one of these objects, even from thousands of light years away, could in theory flood a spacecraft's trajectory with a wave of X-rays and gamma rays of unimaginable intensity. In that scenario, the vessel's shielding would offer little more protection than tissue paper. There would be no warning flash, no sound, only the silent ping of radiation sensors spiking into the red before systems began to fail. This transforms the dream of galactic exploration into a journey through a minefield of high-energy physics. It means plotting a course between stars is not just a matter of fuel and distance, but of cosmic hazard assessment, requiring future navigators to map not only the stars but the graves of stars and to steer wide of their lingering fury. The freedom of the cosmos comes with a sobering price, an acknowledgement that some paths are barred not by walls, but by invisible storms of atomic fury left over from stellar deaths that occurred eons ago. Our galaxy is not a tranquil sea of gentle suns. It is a graveyard, and the tombstones number in the billions. the final terrifying fact is one of sheer, overwhelming scale. Conservative estimates suggest there are over 1 billion neutron stars scattered throughout the Milky Way. Each one is the remnant of a massive star that lived fast and died violently. While many have faded into quiet, cold obscurity over the eons, a staggering population remains active. Hundreds of thousands are likely still spinning as pulsars, their lighthouse beams sweeping the darkness, and a smaller but significant number retain the monstrous magnetic fields of magnetars. This means these engines of extreme physics are not rare cosmic oddities. They are a standard, common product of stellar evolution, as fundamental to the galaxy's life cycle as the birth of new stars. Our solar system, with its stable sun and orbiting planets, is not the galactic norm. We are moving through a spiral arm littered with these dormant and active cosmic landmines. Each one at any moment could experience a crustal shift, a magnetic reconnection, or a final collapse. Their silent, overwhelming presence changes our perspective entirely. It underscores that the universe is not, at its heart, a place of quiet equilibrium. It is fundamentally a realm of violence and extremity, where matter is routinely pushed to absolute limits. Earth's peaceful, life-nurturing corner is the profound exception, a rare and fragile oasis in a desert of nuclear furnaces and gravitational nightmares. The sheer number of these objects tells us that the terrifying powers we have explored are not the whispers of a distant, alien cosmos. They are the background hum of our own home galaxy, a constant reminder that we exist in the calm eye of a perpetual storm. These objects are not cosmic anomalies, but fundamental expressions of the universe's extremes. Every terrifying fact we have explored, from the 2-billion-ton sugar cube to the intergalactic radio scream, points toward a single, unifying truth. Neutron stars and magnetars are nature's ultimate stress test. They are cosmic laboratories where the laws of physics are stretched, twisted, and sometimes broken under conditions we can never hope to recreate. They challenge our most cherished theories, forcing us to confront the bizarre behavior of matter when atoms cease to exist and quantum rules govern objects the size of a city. In their relentless gravity and impossible magnetism, we see the universe's dual capacity for breathtaking creation and utter annihilation. They are the forges where gold is born and the engines that can sterilize a sector of space. They are clocks of impeccable precision and sources of enigmatic signals we are only beginning to decipher. They warp the fabric of space-time itself, slowing time near their surfaces and sending ripples through the cosmos when they collide. To study them is to do more than catalog stellar tombstones. It is to probe the very bedrock of reality, to ask questions that bridge the unimaginably small world inside a neutron and the vast galactic structures we see in our telescopes. They remind us that our peaceful corner of the cosmos is a rare and fragile exception. The true background hum of the galaxy is the slow spin of a billion dead stars, each one a monument to catastrophic beauty, and a promise that the universe operates on a scale of power and violence far beyond our daily comprehension. In understanding these monsters, we ultimately come to understand the extreme and magnificent forces that shaped our very existence. The silent guardians of these secrets are not passive. They are active participants in the cosmic story, their very existence a testament to the universe's capacity for both creation and ruin. From the teaspoon that weighs as much as a mountain to the magnetic field that can erase a planet from halfway across the galaxy, these objects exist to challenge our understanding. They are terrifying in their raw, destructive potential, yet they are also awe-inspiring in their intricate complexity and the profound physics they reveal. Each new observation, each flicker of a pulsar or spike from a magnetar, peels back another layer of a deep and enduring mystery. These discoveries do more than add to a catalogue of facts. They actively reshape our perception of what is possible, forcing us to rewrite the rules of matter, energy, and time. So the next time you gaze up at the seemingly tranquil night sky, remember this hidden truth. Among the gentle, twinkling lights are the ghosts of titans, stellar remnants holding the universe's most extreme secrets in their impossibly dense hearts. Their silent vigil is a constant reminder of the beautiful, violent, and magnificent forces that sculpted our very existence. If this journey to the edge of physics has captivated your curiosity, be sure to subscribe for more explorations into the universe's greatest enigmas. We would love to hear from you. Which of these 25 facts left you the most awestruck? Share your thoughts in the comments below.